I'm going to go over lecture slides today. So if you go under course resources, the second section of lecture slides, it's the last one. It is phases and intermolecular forces, chapter 12. So I'm going to review a little bit of information relating to heat and energy and tie that in with how compounds make phase changes. And then we'll talk about what it is that causes molecules to attract each other. So that's the plan for today. Right. So we're looking at the slide for kinetic energy and potential energy. We talked about the balance between the energy available at room temperature, the thermal energy, compared to the kinetic and potential energy that's present in the substance itself. All right, so that balance between the thermal energy that molecules are getting and the energy that's holding them with their closest neighbors in the substance. Okay, so in the gas phase, there's a lot of kinetic energy and there's not much holding them together. They're not interacting with their nearest neighbors. But in the liquid and solid, they have lots of nearest neighbors. So lots of close molecules that they're interacting with. And we talked about those different kinds of interactions. So in solids, they're just vibrating. There's not a lot of motion. In a liquid, they can slide past each other through space. So there's more energy of motion, but also a lot of attraction with their nearest neighbors, like passing through a crowd. But in gases, they're just completely random motion, not interacting with any other particles. I'm going to skip through some of this stuff. We've been through it. When we reach the point at a solid where they're vibrating so much they have the same energy as that same temperature moving past each other, then that energy is absorbed and it breaks the solid network and allows it to go to the liquid without a rise in temperature. At that transition, they have the same average kinetic energy, and the molecules are able to melt and go into the liquid. We're really balancing the energy of heat from the environment with how much does it want to stay next to its nearest neighbors as opposed to move through the solid into the liquid. So we saw our heating and cooling curve. We drew one of these ourselves in class. In the liquid, we still have a lot of nearest neighbors, a lot of attractions that hold the particles with their friends, right? It's like that's the party is in the liquid, where you can move around, but everybody's interacting very strongly. Now at that interface, I don't know about this picture, but if you think about the surface of that liquid, when we're considering how much energy to go into the gas phase, we're going to escape all of those friends, all of those nearest neighbors to go be alone. And so we have to think about what is the attraction that holds those particles together. Is it a good party? Are there very interesting people? Or are they all the same and you know them very well already and you just kind of want to leave? There's not a lot of attraction to stay. So it's that same kind of a balance, same thinking about what are the attractions between particles compared to being completely isolated. This is a good picture. I like this picture because it shows that surface, and this is water. This is showing a container. It's closed. So if you leave it there long enough, there's going to be a certain amount of water vapor. It depends on temperature, but there will be a certain amount of water vapor over the liquid. And when you reach that amount, what we see is that the number of particles that go from the liquid out into the gas phase equals the number of particles that come from the gas phase. They bump into the surface and they're like, oh, hey, I'm going to stay with my friends, right? So there's an equal rate of going out into the gas or back into the liquid. And that balance is really what tells us something about the molecule and about the boiling point of that substance. When we think about going from a lower energy phase of matter, solid to liquid or liquid to gas, when we go up, we're thinking about the energy, the thermal energy, the heat having enough energy to move it from that condensed phase into the next higher phase. So usually that involves breaking intermolecular forces, interactions between two different particles. It's not like you leave the party and your arm is ripped off, right? It doesn't break the bonds. It's like the interactions between two different people are severed to go be alone. Just an analogy to think about these energy considerations. The forces that hold the molecules together are considered intermolecular forces, so I write IMFs. They're also called cohesive forces. Cohesive is holding together. And if we can look at the polarity of a molecule, we can predict pretty well how strong their cohesive forces are. So I want to get to, yeah. I also like this picture where we're looking at the energy to go to that vapor is equal and opposite of the energy to condense back down. So we've seen some of this already. So when we look at that phase change, we have to consider the two different kinds of interactions. We have the bonds holding the atoms together, and we have the intermolecular forces between two different molecules. In this case, we're looking at two different molecules of the same type. So that is the intermolecular force between two different molecules, right? So that's like these water molecules, they have very strong intermolecular forces. They really like spending time with their nearest neighbors, with their friends. What are these interactions that hold them together? These are so important. They are the same kind of things that allow us to smell or taste. These are physical interactions like a lock and key, where we have a complicated receptor and a molecule responds. So it's very interesting. It's a physical interaction between molecules. So what are they? Most of the forces that hold molecules together have to do with separation of charge. And the size of the interaction is going to depend on the size of that charge separation. So the strongest one is ion-ion charges. We talked a little bit about transferring electrons, and then that positive charge is attracted to the negative charge in an ionic bond. So that is a full charge with a full charge, and that's a chemical bond. But we also have interactions that are very important that are not due to a full charge. They have to do with partial separation of charge. So that would be for our polar molecules. So this is where your skills come in, because we know how to draw the molecule. We know how to look at the difference in electronegativities to identify the bond dipoles, and we know what the shape looks like, so we can decide if they stay polar or if it's a non-polar molecule that they all cancel out. And that will help us predict how strongly they interact with their nearest neighbors. So if it has a permanent dipole, it's going to have a pretty reasonably strong interaction. Okay, so the larger the charge, the stronger the interaction. The bigger the dipole, the bigger that favorable interaction. But even nonpolar molecules attract each other on the basis of charge separation. And this is where it gets a little bit hard to envision. It's a little bit abstract. And so I like to look at data, like who came up with this and why did we have to come up with this? Who thinks this makes any sense? So we're going to look at data to really understand why we need this kind of explanation. So these are typically called London dispersion forces or dispersion or van der Waals force or lots of names. So I have arranged these from weak to strong, and we're going to look at the weak ones first. So the weakest one is dispersion, or you can think of it as induced dipole. It's not a permanent dipole, it's just a reaction. It's very short in time, just a short moment in time. And these happen for hydrocarbons. Remember, carbon and hydrogen have a non-polar bond, so hydrocarbons are non-polar. So If a compound has attractive forces that are only based on dispersion, they're going to have a low boiling point. It means it's very easy. It does not take very much heat. It's easy to get it into the vapor phase. And what that means is we can smell it. Volatile means that you can smell it. You know, you just waft it towards you and you can smell the substance. So maybe you can think of things like gasoline. If you pump gas, you can smell it. It's not so good for you, but you can smell it just from the pump. Or a fingernail polish remover, you can smell it. It's volatile. That means it's pretty easy at room temperature for that energy to take the molecules into the gas phase and come and hit your nose. Now, as we go from weak to strong, if we have a separation of charge, such as a polar molecule, then those molecules will line up head to tail, plus, minus, and that makes a stronger interaction. They want to stay with their friends. So you need a little bit more heat to get it to come away from its friends, go into the gas phase to smell it. So dipole-dipole is a stronger intermolecular force than dispersion or London forces. Now, the most extreme case of dipole-dipole forces is called hydrogen bonding. This is not a chemical bond. It's just the way the word is used. It's just tradition. It's technically incorrect. But hydrogen bonding is an intermolecular force between two different molecules. It's not a chemical bond, even though bond is in the name. So hydrogen bonding is a very special dipole-dipole force. It is between a lone pair and a hydrogen, but the lone pair has to be on nitrogen, oxygen, or fluorine, and the hydrogen also has to be on nitrogen, oxygen, or fluorine. Okay, so it's very special. It's responsible for the unusual properties of water. Water is a completely unique substance because of extensive hydrogen bonding. So we'll take a look at that in terms of data as well. So there's kind of the overview, what we are looking at with intermolecular forces. So let me start with the weakest one that is the most abstract, and that is dispersion. London dispersion, London forces, or van der Waals forces. So van der Waals forces are based on polarizability, a disruption to the electron cloud. So if you look at the 1s, we have a spherical electron cloud. 2s is bigger, 3s is bigger, it's still spherical. But when it gets bigger, it's easier to push it around. So one thing that that I think of with this is the cotton candy picture. When I was a child, you know, these things are huge, and it would just get all over. It would get in my hair. It just spreads everywhere. So it's kind of like that. If it's bigger, it's easier to bend it out of shape or to get it everywhere. So when we bend it out of shape, that creates an instantaneous separation of charge, an instantaneous dipole. Just for a moment, just bends it out of shape, and then it goes back. So that ability to be bent out of shape is polarizability, and that is what leads us to explain the data for nonpolar molecules. No permanent dipole, just a big electron cloud, gets bent out of shape, and then it attracts its nearest neighbors, right? They get bent out of shape, they have a charge attraction. So here's a little animation. I have my nucleus has a bunch of positive charge, and the electron cloud around it has a bunch of negative charge. Now these two, let's say they're noble gases, they're like neon. So they come together, there's no dipole, it's just one atom, but the nucleus of one attracts the electrons of the other, and they get bent out of shape. And then it's out of balance, right? So it's going to respond by polarizing the other one. It's kind of like it sloshes around. There's a disturbance, it sloshes around. Here it's going to respond the other direction. And then eventually it just calms down, it just settles. Okay, so that is the instantaneous dipole. that is what gives us the dispersion force. So what we see in our dependences is the dependence on size. And we can estimate the size of the electron cloud by looking at the molar mass, right? As we add electrons, the mass goes up because of the protons in the nucleus. So we're going to use molar mass to estimate how big is the electron cloud. So let's take a look at some data. Here are the noble gases, and here are the molar masses in grams per mole. And we have the boiling point. So the boiling point, remember, that's how much energy it takes to go from the nearest neighbors into the gas phase all by themselves. And these are all very low temperatures because these exist as gases. They're just one atom. But look at the dependence on the boiling point in Kelvin. So very cold temperatures. Helium is a gas all the way down to 4 and 4.2, very close. As we go up to neon, the molar mass is 20. Its boiling point is 27 Kelvin. Still very cold, but it's roughly proportional. Argon has a mass of 40, boiling point of 87. Again, it goes up a bit more, but it's still on the same order of magnitude. As we double the mass, we get a larger boiling point. So it looks, they go together, right? It looks like they scale together. So there's one set of data that supports something relating to the size that causes these to attract their nearest neighbors and stay together. Let's take a look at our hydrocarbons. So these are just carbon and hydrogen. There's no dipoles in the molecule. It's completely nonpolar. They completely, in the geometry, those tiny dipoles cancel out anyway. Completely nonpolar. So pentane has 5 carbons, hexane has 6 carbons, heptane has 7, octane has 8. Here are the molar masses, and they go up. And then here's the boiling point. They go up too. It looks roughly linear. So we see not just for atoms, but also for molecules, we see a similar dependence in the boiling point depending on the molar mass, right? They just scale together. So let's take a look at our halogens. Here's fluorine. Fluorine is a gas, 38 grams per mole. Chlorine is 70 grams per mole and it is also a gas, a yellow gas. Now we get to bromine. Bromine has 160 grams per mole and we begin to see liquid. Lots of gas, but also liquid. So what is it that's special about bromine? Why is there a big jump there? So we can take a look at the periodic table, right? We go from chlorine here, whoa, it's over on the side. Chlorine over here to bromine here. What's the big difference? We have that whole set of D electrons. We have all of those transition metal electrons. So we see a big jump in the mass, and that's where we go from seeing gas to liquid at room temperature. Now if we go one more, we look at iodine, it's actually a solid at room temperature. So again, we're seeing that dependence. If it has a large molar mass, it wants to stay together with its friends. If it has a small molar mass, it's easy to get out and escape into the gas. Okay, so the more atoms, the more electrons. The more electrons, the bigger the electron cloud. The bigger the electron cloud, the easier it is to bend it out of shape and cause a momentary separation of charge. So I have some values for energy in here. I just left them in. You're not required to know or understand them, but just for people who like to see the values, we can think of dispersion as weak, the weakest intermolecular force, and it has 0.05 to 10 kilojoules per mole. It's a pretty wide range. If we look at dipole-dipole, it's even stronger, but there is some overlap. So some dipole-dipole interactions are weaker than even a very strong dispersion. So there's some overlap there. But dipole-dipole goes from 5 to 25. It's pretty wide range again, and that even still overlaps with hydrogen bonding, that special kind between the nitrogen, oxygen, and fluorine. And then compare that to covalent bonds. So covalent bonds like H2 bonding. Those are even stronger, right? So that's where we get into chemical bonds versus intermolecular forces. Intermolecular forces are weaker, but there's so many between all those different molecules that they're very important. We can compare that to about 300 Kelvin is a warm room, a little bit, maybe a little hot, and that provides about 3 kilojoules per mole. So for something that has only dispersion, it can get into the gas phase and we smell it pretty easily. If it has a dipole, it's a bit harder to get into the gas phase, and so we don't smell it quite as much. This is really a summary slide, just to give you an overview of dispersion forces in words. Now the next weakest intermolecular force is the dipole-dipole interaction. So for a molecule like HCl, it has a permanent dipole. It is a polar molecule, so it will interact favorably with other polar molecules. It will line up the plus side next to the minus side, and so on. So that tends to give it a higher boiling point. It takes more energy to get it into the gas phase by itself. Here's some information, here's some data. So we're looking at ethane, there's that hydrocarbon, so completely nonpolar. And then here's formaldehyde, and it has a polar bond. They have exactly the same molar mass, so they have exactly the same amount of dispersion, but they have different boiling points. Now this is degrees C, so it's not as handy to think about energies as Kelvin, but the value of the degree is the same. So we're looking at going from basically minus 90 to minus 20, 70 degrees C or 70 Kelvin difference in energy to get it into the gas phase. That's about how much we get from the CO bond dipole. So we can see from that boiling point that the dipole affects it. It's more favorable for that formaldehyde to stay near its nearest neighbor. Dipole-dipole forces in the liquid, they jumble around. There's attractions, there's repulsions. But if the molecule has a larger dipole, it's going to have a more favorable attraction. Therefore, it will take more energy to pull it apart into the gas. Now, here is an interaction, and I put it right between the strength. This is not really an intermolecular force because ions are technically not molecules. So this is between a full charge, right? We have a dipole-dipole, but now we're going to talk about a full charge with a dipole. And so we see that ionic compounds, they separate into ions, and they can still interact favorably with dipole, with polar solvents like water. So here I'm showing how we have a positive ion, maybe a sodium ion, and it is the waters are going to line up their negative oxygens, those negative side of the dipole, towards the ion. Now for every sodium that dissolves, there's a counter ion, maybe a chloride. So that chloride ion is also going to interact favorably with water, but this time water is going to point its positive dipole, the positive end, the hydrogen end of the dipoles, towards the chloride ion. So in that way, water helps stabilize sodium and chloride. So this becomes important when we look at whether something will dissolve in another substance, usually water. So ion-dipole interactions. They're technically not IMFs, but they're interactions. I'll be listing them separately right next to metallic bonds. Because metallic bonding, again, it's not polar covalent, it's not ionic, it's its own thing. Just metals with metals. All right, so when we have, okay, the next one is hydrogen bonding, right? This is showing an extensive network of the dipole here and the dipole here, but very specifically the electrons on oxygen interacting with the hydrogen on oxygen. So hydrogen bonding. Why do we need to make hydrogen bonding different from dipole-dipole? Like, why do we need to have this special case? Well, if we look at the data, What we see here are the period numbers. So this is as they get bigger, right? This is N equals 2. We have carbon, nitrogen, fluorine, and oxygen. Then in group 3, we have silicon. Instead of carbon, we just went down. Phosphorus instead of nitrogen. Chlorine instead of fluorine. And sulfur instead of oxygen. And so when we go down, we see that the electronegativity went down also. And these all, as we keep going down the periodic table, these all have a very linear kind of slope, right? They go together. It looks like they go together. But when you get to these, they break the pattern. So you can see water is way up here. It has a freakishly high boiling point. Why is a boiling point 100 degrees for such a small molecule? I mean, that's crazy. Ammonia also has a remarkably high boiling point, and HF as well. HF is special because fluorine is so special. Anyway, so these are just much higher than we would expect based on all of the other behavior of the compounds. And so we need to come up with some way to explain that, some way to understand what's happening. And that is why we introduce hydrogen bonding. The key to hydrogen bonding is that it requires these bonds. It requires an NH bond, an OH bond, or an FH bond. Hydrogen bonding is the interaction between two different molecules of the lone pair on one of those atoms and the hydrogen that's also on one of those atoms, NO or F. Water has two lone pairs, and they give the glue, the interaction, they give the bond. So we have two donors, and then we have two hydrogens that can accept that interaction. So in water, we get 2 hydrogen bonds per mole of water. If we look at ammonia, ammonia just has 1 lone pair. It has 3 hydrogens, but only 1 hydrogen can accept a hydrogen bond from the next molecule. Ammonia has just 1 hydrogen bond per mole of ammonia. And that's why water was so high. It's got 2 moles of hydrogen bonding per mole of water, whereas ammonia can only do 1. 1 favorable, successful hydrogen bonding interaction. In water, we have an extended network in 3 dimensions. So we're looking at these dots. These are the hydrogen bonding interactions, and they are so extensively networked that it's very stable. It takes a lot of energy to take this water, right? This is interacting with a bunch of nearest neighbors. It's like, I don't want to go home, Mom. I'm staying at the party, right? A lot of favorable interactions. It also leads to water's unique properties. At the end of this set of slides, which we don't really usually get to, but you can see some that talk about the viscosity, like how thick the liquid is, and the surface tension. If you've seen like bugs can sit on the top of water, it's because it interacts so strongly with other water molecules. Hydrogen bonding is also really important in biology. If we take a look at this, this is holding the helix together, the secondary structure of this big long molecule. And we usually see in chemistry 3 bonds of interactions. So let me take a look at this hydrogen. And normally it can just interact 1, 2, 3. So maybe it could interact with this group, or 1, 2, 3. No, that one's too far. Let's look at how far away this hydrogen bond is. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 bonds away. It's interacting with an atom that's 12 bonds away, which is amazing. So it's holding it together with that hydrogen bonding interaction. It's very important. Here's another example of how important hydrogen bonds are. This is holding 2 spirals together like a zipper. So what happens is the very first ones that find each other, it's hard to find. Like if you're trying to do a zipper, getting it started is much harder. But once you start going, these just zip right up. And the strength of that connection depends on the 2 bases involved. So for example, adenine and thymine have 2, right? This has 2 hydrogen bonds between them. Cytosine and guanine have 3. So the CG pairing is stronger than the AT pairing. But they're both, really important. So hydrogen bonding. This is an oxygen with the lone pair interacting with the hydrogen. This is on a nitrogen. So the hydrogen has to be on an N, O, or F. Here's an O. This is hydrogen on a nitrogen. So don't be confused between the covalent bond inside the molecule, the polar covalent OH bond inside water, and the hydrogen bond between 2 different molecules of this same type. So intra, very close words. So I will usually use the words of like a chemical bond or an intermolecular forces, IMFs. That's between 2 different molecules. And again, about that energy. Now, if we want to consider how 2 substances will dissolve in one another, will they interact favorably or will they stay with their own kind? Will they mix or stay apart? That depends on their interactions with the other molecule. So they will usually interact favorably if they have similar structural elements. If they have similar structures, they'll have similar intermolecular forces. If they have different kinds of intermolecular forces, they don't interact favorably. They want to stick with their own kind. But if they have similar structural elements, then they will interact favorably. So here we're looking at ethanol. This is alcohol. It's got 2 carbons. So this area is nonpolar, but then the OH is polar. And the OH has hydrogen bonding. So alcohol can hydrogen bond with water, and it will dissolve in any proportion, right? This is just like vodka. This is just like making your mixed drinks. It doesn't separate out. It mixes in any proportion because they have hydrogen bonding that pulls them together. So they interact favorably together. Here is glycerol. Glycerol is used in soap, a lot of times like glycerin soap. It has 3 carbons and each carbon has its own OH on it. So again, that OH-OH interaction results in hydrogen bonding. It's very favorable. So here are some examples. So remember, hydrogen bonding occurs in a molecule that has hydrogen attached to N, O, or F. So not just having any N or any O, it has to have a hydrogen on it. So here is a summary. Going from weakest, stronger, right? Dipole-dipole interactions have permanent dipoles, all the way down to hydrogen bonding. And then here it is as a decision chart, just a grid. All right, anything else? Oh, this is a really good one. Let's go ahead and work this problem. So look at number 1, butane. I like to start with the weakest interactions and list everything that it has. So for butane, what is the kind of intermolecular force does it have? For butane, it's got 4 carbons and it's just got carbons and hydrogens. It has dispersion, and that's all. There's no dipoles, so we're done. Let's look at HCN. What about that one? It has a little bit of dispersion because it's a molecule. They all have a little bit of dispersion. Does it have a dipole? Yes, it does. It has a dipole going from carbon to nitrogen. Nitrogen is more electronegative than carbon, so this has a dipole. So yes, this has dipole-dipole forces, and I'm just going to write DD, dipole-dipole. Does it have H bonding? So this is a tricky one.
No, because it's not bonded to oxygen.
Yeah,
Right?
nitrogen bonded to the carbon, but not to the hydrogen.
Yes.
Okay, so that means yes or no?
No.
No H bonding
bonding.
because
Yes.
the H is
Hydrogen
on
should
the
be
carbon, not on the
yes, not.
nitrogen. Yeah, great. So here's the H. Here's the H, and then the black one is carbon, and then the nitrogen's over here. So the nitrogen could donate the H bond, but there's no hydrogens that can accept it because carbon does not share its hydrogens. It keeps it. What else have we got? For number 3, carbon dioxide, it has a little bit of dispersion. Does it have dipole-dipole forces? Let's look at those dipoles. So let me draw some in. There's a dipole between the carbon and the oxygen, and a dipole between the carbon and the oxygen.
It's going to be non-polar.
Yeah, it ends up being a non-polar molecule. So that's it. No dipole-dipole forces. Because the molecule is non-polar. What about glucose? It's going to have some dispersion. Does it have dipole-dipole?
Yes.
It's got all those dipoles on the OH. So it does have dipole-dipole. Does it have hydrogen bonding?
Yes.
Yes.
Yeah, it has hydrogen bonding all over. All of those O's and H's. So let's think about it. Butane is a gas at room temperature, right? If you put it in your lighter and you let it out, it goes to the gas phase. HCN is also a gas, has a little bit of dipole-dipole. Carbon dioxide is a gas. What is glucose?
Sugar.
Yeah, that's sugar. That's a solid. That's a crystalline solid at room temperature. So all of those strong interactions, hydrogen bonding, hold it together as a solid at room temperature. Yeah, so we get a lot of predictive power by looking at the intermolecular forces. Yeah, here's just another question looking at that dipole-dipole. These have exactly the same molar mass. So compare the boiling points. What do they have? They have exactly the same amount of dispersion, right? Exactly the same amount. What about the dipole? Do they both have dipoles?
Yes.
Yeah, they both have dipoles on that COOH, CO bond. Now, what about the shape? Right here, the angles at this oxygen are what?
It should be bent, I guess.
Yeah, bent. This we're calling less than 109.5. Now this one is the same, right? 2 bonds and 2 lone pairs, same shape. All right, but what else?
Hydrogen bonding.
Hydrogen bonding?
The bent one has hydrogen bonding, but the other one has no.
Oh, they're both bent. But what else? Which one has a higher boiling point?
It's gonna be the first one.
Why?
Because it has hydrogen bonding.
Yeah,
because
this
hydrogen
one has
is
hydrogen bonding.
Yeah.
It has lone pairs and a hydrogen on oxygen. This one has no hydrogen bonding. It could give a hydrogen bond, but there's no hydrogens to accept. So no hydrogen bonding. Let's look at those boiling points. Very different boiling points.
I have something.
So wait, Professor, these are 2 different molecules of the same. Is this called the same thing? What is this?
These are isomers. These are structural isomers.
Oh, right.
So they have the same atoms, but they're arranged differently. And that different arrangement, so here, this is symmetric and there's no hydrogens on the oxygen. This is called an ether. This is ethanol, good old vodka. This is ethanol, it's an alcohol. And that hydrogen bonding gives it a very different boiling point than the ether. So here we're looking at the pressure. I think, did we talk about the manometer and how these are formed? Here inside, we're putting a closed tube inside mercury because it's a liquid metal. It's very heavy. Then we lift it up. Now, if there's nothing inside, then that mercury will be 160 millimeters tall. Now, if there's something in there that has intermolecular forces, right, it's going to have a different pressure inside. That's called the vapor pressure. I don't know, I guess I like to explain this more in terms of that closed flask, where we just have water, we close it, and the water is going to reach a certain amount of vapor inside. So if a compound has really strong interactions with its nearest neighbors, that means it's going to have a lower vapor pressure, right? It's going to stay in the liquid at a higher temperature. So if it has strong intermolecular forces, it has a lower vapor pressure and a higher boiling point. Melting point and boiling point go together, so it's going to have a higher melting point and a higher boiling point. So that's a really good way to remember. And I think I put this in the worksheets too. I'll draw it when we do the worksheets. All right. Yeah, this is all the same thing again. Oh, and I like this relative strength. I put this in because a student asked, so I found this 1/4, and I do like it. You can see here's dispersion, dipole forces on the weaker side, hydrogen bonding, and then for these chemical bonds, there's a lot of overlap. So it's just a general sense of how strong they are. We'll work on this file right here. Worksheet number 6, intermolecular forces.